This is the problem-solving session for Faraday's law and Lenz's law, and here are the 5 problems that we looked at in class. Number 1 says a single loop of wire with an area of 0.0740 square meters is in a uniform magnetic field that has an initial value of 3.8 teslas, is perpendicular to the plane of the loop, and is decreasing at a constant rate of 0.170 teslas per second. So, probably not required to solve this problem, but I always like to try to sketch what's going on here. So I have my single loop of wire that has a cross-sectional area. It's in a magnetic field, and we don't know the direction, but we're really just after the magnitude of the EMF anyway. So I'm going to imagine that the magnetic field in this region is upward, perpendicular to the plane of the loop. So here's the magnetic field, and it initially is 3.8 teslas, and we know that it's decreasing as well. So part A asks us what EMF is induced in this loop. Well, Faraday's law says that the induced EMF is equal to the negative of the number of turns in a coil or a loop times the rate of change of the magnetic flux. And this is an average EMF. If you want to do the EMF at an instant, you got to do some calculus and turn this into a derivative. And magnetic flux itself is defined as the product of the magnetic field, the cross-sectional area, and then the cosine of the angle between the direction of the magnetic field and an axis that passes through the loop perpendicular to the plane of the loop. So I'll sketch that on there. If you put both of those things together, you can write that the EMF is equal to minus n times the change in BA cosine theta over the time interval. And in almost every one of these problems I've ever seen, only one of the factors is changing, which is causing a change in that magnetic flux. In this case, it's the magnetic field that's changing, which means area and the angle between the magnetic field and the loop are the same, and those are constants. They can come out of here, so I can write this as minus n times area times cosine of theta times the change in the magnetic field with respect to time. And from that point, we should be able to do the calculation. So the number of turns is 1. The cross-sectional area is 0.0740 square meters. The angle between those two is 0, and the cosine of 0 is 1. And then the change of magnetic field with respect to time is 0.170 teslas per second. And if we put that into a calculator, we get 1.26 times 10 to the negative 2. And you could leave it in Tesla meters squared per second, but it's an induced EMF. It's going to also be able to be written with units of volts. And I have a minus sign here, but since it's just asking us for the size, I'm really just going to treat this like I'm doing the magnitude of this and leave my answer as positive. The negative sign in Faraday's law is really useful when you're working out what the direction of things are, and the problems in the second half of this problem set are focused on that idea. Part B says, if the loop has a resistance of 0.8 ohms, what is the current induced in the loop? So here we're jumping back to our stuff from the circuits unit, Ohm's law specifically, saying that current is equal to the potential difference across something divided by the resistance. Potential difference has units of volts. This induced EMF has units of volts. So we're going to plug that in, 1.26 times 10 to the negative 2 volts. The resistance of 0.8 ohms I get 1.57 times 10 to the negative 2 amps, or 15 milliamps of current. The second problem, pretty similar. In a physics laboratory experiment, a coil with 230 turns enclosing an area of 13.1 square centimeters is rotated in a time interval of 4.4 times 10 to the negative 2 seconds from a position where its plane is perpendicular to the Earth's magnetic field to one where its plane is parallel to the field. The Earth's magnetic field at the lab location is 5.8 times 10 to the negative 5th Teslas. So what's happening in this particular situation is we're going from an orientation, if this is Earth's magnetic field, I start out with my coil with the plane perpendicular to that. So here, and I'm not going to try to draw 230 turns of my coil, but something like this. And then the axis of my coil would be in this direction. And then I am rotating it so that the after picture, the coil is sitting here. Try to draw a neater coil this time. There, in this orientation. So I've rotated it by 90 degrees. All right, and the rest of the things are numbers that we know. What is the total magnetic flux through the coil before it is rotated? Well, magnetic flux is equal to the magnetic field times the cross-sectional area times the cosine of the angle between the axis of that area and the magnetic field. So that is 5.8 times 10 to the negative 5th Teslas. The cross-sectional area is 13.1 square centimeters, but we're going to have to do a little bit of conversion. There are 100 centimeters in 1 meter, so that means there are 100 centimeters all squared in 1 meter squared, which means this is going to be 13.1 times 10 to the negative 4 square meters for cross-sectional area. And the initial angle between that axis and the magnetic field is 0, so cosine of that is 1, and that makes a fairly small number for the magnetic flux. I get 7.6 times 10 to the negative 8, and the units of flux are Tesla meters squared, but that is also, as the book points out, a Weber. So I'm going to use Webers for my units here. Part B, what's the total magnetic flux when the coil is rotated? Well, here the big change is that the magnetic field's the same strength, the area is the same strength, but now the angle is 90 degrees, and cosine of 90 degrees is 0. So our magnetic flux is 0 in this orientation. Finally, what's the average EMF induced in the coil? The average EMF, according to Faraday's law, is minus N times the change in flux with respect to time. Again, we're just looking for the magnitude, so I'm going to just do absolute values here. I have 230 turns. The change in my flux is going from 7.6 times 10 to the negative 8 Webers down to 0, so the magnitude of that change is 7.6 times 10 to the negative 8. And the amount of time this is rotating in is 4.4 times 10 to the negative 2 seconds. And so that number comes out to be 3.97 times 10 to the negative fourth volts. So you can actually induce an EMF. You can make a very rudimentary electric motor by having a coil and spinning it around in Earth's magnetic field. However, Earth's magnetic field is not super strong, and so if you look at this, 230 turns is not an insignificant amount of turns in a coil of wire. You're turning it pretty rapidly if it's just taking you 0.04 of a second to go a quarter turn. So that's going to be just over, well, it's going to be, I don't know, 16 16 tenths of a second, I guess, 1600ths of a second rather, to go a whole turn. So you're turning the whole coil several times per second, which is, again, not insignificant if you were going to do that. Then you're only getting less than a millivolt of potential difference out of that coil. Problems 3, 4, and 5 were intended for practice in figuring out directions of things. Half the battle in solving these problems is figuring out, again, how to think about three-dimensional phenomena off of a two-dimensional picture and what direction everything is oriented in. The problem reads, using Lenz's law. So Lenz's law, one way to think about it is it explains the minus sign in Faraday's law. Determine the direction of the current in resistor AB of the figure when switch S is opened after having been closed for several minutes. So if switch S is closed, I can use my knowledge of circuits on this left-hand coil to reason, okay, the current will flow out of the battery through the resistor, up the back of the coil, and then down in the front. So the current in this coil is going along like this in the front and the opposite direction in the back. And I can use a number of right-hand rules, but there's a right-hand rule for current going around a coil, which is the fastest route here, which is to say, if this is the rod of my coil and I wrap my fingers around it in the direction that the current is flowing around that coil, my thumb points in the direction of the induced magnetic dipole. So let's use red here. This will make a magnetic field in this coil and in this, what I assume is an iron or steel core, that is pointed to the right. So that's the magnetic field that's being created by the current flowing in the circuit here on the left, which will also extend over to this region, and it will put a, there'll be a magnetic field through this one. It's getting weaker with distance, but it's still in that direction. However, when we open up the switch and this current turns off, this magnetic field over here is weakening with time. And the fact that the magnetic field is weakening in time means that the induced magnetic field in the right-hand coil is going to point in the same direction to try to fight against that change that it's undergoing. So if the induced magnetic field is pointing to the right, that means the current has to go up and back and down in front of this coil. So if I have current going down in front, that means current is going here and here and here. So the current is going left to right, or from A to B through this resistor. Scenario 2, when coil B is brought closer to switch A with the switch closed. Well, we've already done the reasoning about this. This produces a magnetic field in here, and just like a bar magnet, that magnetic field gets weaker with distance. So if we draw these field lines spreading out for that magnetic field, if I bring this piece of the system closer, the magnetic field, the external magnetic field, the magnetic field from the other coil that this one is experiencing, is pointing to the right, and it's getting stronger, and that's a change in magnetic flux. So this coil is going to try to produce its own, it's not going to try to, it does, it produces its own magnetic field that is in the opposite direction to that external magnetic field. And if the magnetic field points to the left, that's current that's coming up in front and down and back, down here, across and up. So from B to A in this particular situation. Finally, when the resistance is decreased while the switch remains closed, so I have the switch now remaining closed, so my current's flowing here, and again down in front of this particular coil, producing a magnetic field again that is oriented to the right here. When the resistance is decreased, so this is a symbol for a variable resistor. If you have any old stereos that have an actual knob that you turn, there's a variable resistor embedded in there. So I'm making this resistance smaller. Well, from our circuit's reasoning, if we make the resistance smaller, the current is going to increase. The current increasing means this magnetic field is getting stronger with time, and as this magnetic field gets stronger, that increases the magnetic flux through this coil. This coil is going to induce a magnetic field in the opposite direction, which is just what we saw in the previous situation, which again is going to be current flow in the direction shown from right to left through the resistor, or from B to A. The fourth problem was a situation where now we were looking down on the coil, and I picked these problems because they have different perspectives, and again, one of the big challenges is figuring out how to visualize all this stuff three-dimensionally when it is drawn two-dimensionally. It has a small circular ring here inside a larger loop that's connected to a battery and a switch as shown in the figure. Use Lenz's law to find the direction of the current induced in the small ring just after the switch S is closed. So if I close the switch, I'm going to get a current flowing around my outer loop in a counterclockwise direction. Around that loop, that's going to produce a magnetic field that's pointing out of the page. So the out of the page vector convention is to draw a series of dots to represent those vectors. So this is the magnetic field produced by the outer loop. And since there was previously no external magnetic field in the center of this ring, but now there is a magnetic field and it's increasing briefly for a time while the current is getting going here in the circuit, then this ring wants to produce its own magnetic field to oppose that change in flux. So the magnetic field from the inner coil is going to be in the into the page direction, and the into the page direction means I have to have clockwise movement of current in my coil. B says use Lenz's law to find the direction of the current induced in the small ring after S has been closed a long time. Well, after S has been closed a long time, the current flow around this loop is going to be steady, which means the magnetic field produced here and sketched in red is going to be constant, and that means there's going to be no change in magnetic flux through this inner ring, and therefore you get no induced current. Again, you have to be changing something in order to induce a current in this pickup ring here. Third situation says use Lenz's law to find the direction of the current induced in the small ring just after S has been reopened. So if we've just reopened the coil here, the current stops flowing, but it doesn't do so instantaneously, and so there are still some external magnetic field here, but this magnetic field is getting weaker with time. It's going away, and this coil, which was had a steady amount of magnetic flux through the middle of it, now is losing magnetic flux from this external ring. So it's going to induce a current which creates its own magnetic field in the same direction that the external magnetic field was in. And that means same direction means the same direction of current flow around this ring. So for a brief moment of time, current will flow the same direction around the inner loop as it was flowing around the outer loop. The last problem in this set had a ring and a bar magnet in a number of scenarios. For each of the actions depicted below, a magnet and or a metal loop moves with a velocity v, and v is constant and has the same magnitude in all parts. Determine whether a current is induced in the metal loop. If so, indicate the direction of the current in the loop, either clockwise or counterclockwise when seen from the right of the loop. The axis of the magnet is lined up with the center of the loop. All right. So, again, three-dimensional is hard, but they put this little thing here, which means I think that the front of the loop, or the left-hand side of the loop, is the out of the page part, and this part over here is the back of the page part. At least that's the convention that I'm. So in the first scenario, I have a stationary loop, and the magnet is going to be approaching. So the magnetic field from this magnet that I'm holding points to the left. Use my pen to symbolize the direction of the magnetic field. So that magnetic field is pointing to the left, and as it's approaching the ring, it's getting stronger and stronger, which is increasing the magnetic flux from that external magnetic field in that ring, which means the ring is going to induce its own magnetic field in the opposite direction. And in doing so, that's going to be current flow that goes down in the front of the ring and up in the back, or in this perspective that's drawn here, I guess we would say counterclockwise around this ring. Scenario number 2, the south end of the magnet is being pulled away from the ring. So if the south end is being pulled away from the ring, the magnetic field at the south end points toward south. So I've got external magnetic field in this ring that's pointing to the right, but as the magnet moves away, that magnetic field is getting weaker and weaker and weaker, which means the induced magnetic field is going to be in the same direction as that external magnetic field. And once again, that corresponds to flow around the ring that is down in the front of the ring, up in the back of the ring, or counterclockwise. Scenario number 3, magnet is held near the ring and nothing's moving. If I have no change in that external magnetic flux, I get nothing happening here. I can't make energy for free, and so that situation has no induced current. Situation 4, I got my magnet and my ring, and here I'm moving them both together at the same velocity. And this movement means that the strength of the magnetic field from the bar magnet at the ring is never going to get any weaker or smaller, or weaker or stronger, because they're going to stay the same distance apart. And this is another situation where the induced current is 0. Finally, in the last situation, I have a magnet and the ring is moving away. So I have a stationary magnet, and now I'm pulling the ring away. Stationary magnet with the north pole means its magnetic field points to the left. If I'm pulling the ring further away, it is getting a reduction in that external magnetic flux, and that's going to cause an EMF in the ring to make its own magnetic field point in the same direction as that external magnetic field did, and that corresponds to flow around the ring that is up in the front of the ring, down in the back of the ring, or clockwise. As always, if you notice an error in these solutions, I'd appreciate you letting me know that.